Hello my dear students, in this lecture we are going to see one previous year GATE numerical on Rankine cycle. This question was asked on the steam turbine. The question was asked in GATE 2015 for 2 marks in set 1. Now let us understand this question. Here one by one we will read the statements. Now the first statement is steam enters a well insulated turbine and expands isentropically throughout. Now here they have mentioned that steam enters means it is a steam turbine, means it is a Rankine cycle, right? Steam turbine means it is a Rankine cycle, and in turbine the expansion is isentropic, means constant entropy. Isentropic means entropy remains constant throughout, right? Now let us understand this. Means we have to draw first Rankine cycle. If I draw temperature versus entropy diagram, temperature on y-axis and entropy on x-axis, now there will be a liquid vapor dome, because it is a Rankine cycle, steam turbine cycle. Now here the expansion is isentropic. Let us say the expansion starts at condition 1. Now let us read the second statement. At an intermediate pressure, 20% of the mass is extracted for process heating and the remaining steam expands isentropically to 9 kilopascal. Now here means from 1 to 2 we are going to expand here, right? Let us say 2 is somewhere here, right? Now my dear students, from 1 to 2 total mass is m. Here total mass circulating is m, but from 2 they are saying that from 2 20% mass is extracted for process heating. Here they have given from condition 2 20% mass is extracted for process heating and remaining steam expands isentropically to 9 kilopascal, right? Therefore from 2 I am going to extract 20% mass. Therefore let us say this mass is extracted. Here this m1 which is nothing but 0.2 m, 20% means m1 is equal to 0.2 times total mass, right? This much mass is extracted for process heating and the remaining 80% mass, we can say the remaining 80% mass is again isentropically expanded, right, like this to the 3 condition, right? Now my dear students, from 1 to 2 the mass is m, but from 2 to 3 the mass is 0.8 m, 80% mass, remaining 80% mass, because 20% is extracted, right? Now let us understand the question. Isentropically to 9 kilopascal. Here they have given that to 9 kilopascal means this condition is at end of turbine, means 3 condition. Therefore we can say P3 is equal to 9 kilopascal. Now let us read the next statement. Inlet to the turbine. Now here turbine inlet is 1. Definitely turbine inlet is 1. Inlet to the turbine. Pressure is 14 megapascal. Temperature is 560 degrees Celsius. Enthalpy is given. Means my dear students, it is the inlet enthalpy of turbine, means it is a H1. Therefore here only I will write this value is H1. Therefore we can say H1 is equal to 3486 kilojoule per kg, and this value will be S1, inlet to the turbine. Therefore here S1 is also given. S1 is equal to 6.6 kilojoule per kg Kelvin. Here H1 and S1 are given. Therefore it is in superheated state. Directly H1 and S1 given means it is in superheated state. Now intermediate state means state 2. Enthalpy is 276 kilojoule per kg. Now my dear students, actually this value is 2776 kilojoule per kg. It is printing mistake. So let us correct this printing mistake. Here I am deleting this value. Here this value actually in examination it is given as, I am writing here 2776 kilojoule per kg. And what they are saying, it is a intermediate state, means it is a state 2. Therefore again this value is H2. My dear students, this value is H2, right? So let us write here. Initially H1 is given 3486 kilojoule per kg. S1 is given 6.6 kilojoule per kg Kelvin. H2 is also given 2776 kilojoule per kg. Now let us go for next statement. Now here exit of turbine means 3 condition where pressure is 9 kilopascal. Here it is given exit of turbine. HF, Hg values are given. Means it is in liquid vapor state, right? It is liquid vapor dome, right? In this dome. Therefore here also the point 3 I have drawn here in liquid vapor dome. Now HF is given, Hg is given, right? Means at 3 we can say at 3. Here I am writing at 3, which is nothing but P3. Here HF is given, HF is 174 kilojoule per kg. Then you can find here HF. Hg is given, Hg is 2574. Hg is also given 2574, unit is same, kilojoule per kg. Then SF is also given, SF is 0.6, right? SF given 0.6, unit is kilojoule per kg Kelvin. Then Sg is also given 8.1. Here Sg is equal to 8.1 kilojoule per kg Kelvin, right? Now again, if the flow rate of steam entering the turbine is 100 kg per second, flow rate of steam entering the turbine means at the entry of turbine is 1, and at entry the mass is entering is m. Therefore total mass, we can say total mass m is nothing but 100 kg per second. Here they have mentioned total mass is 100 kg per second, right? Therefore my dear students, here we can say m is equal to 100 kg per second. 100 kg per second. Here I am writing, right? M is equal to 100 kg per second. So let us write somewhere. M is equal to 100 kg per second. Now the question is, then the work output in megawatt is. Now here, what will be the turbine work output in megawatt? And it is a fill in the blanks. So my dear students, here we have to find in megawatt only, right? You have to take care of units. So let us find this answer. Here we are going to find this answer. Now my dear students, everything is given. Now my dear students, we know that the steam is expanding isentropically from 1 to 2 and 2 to 3. That means we can say S1 is equal to S2 is equal to S3, and S1 is given. Here S1 is given, but S3 we have to find from steam table, that is S3. We can say S3 is equal to SF plus Raynaud's fraction into Sg minus SF, and it is at condition 3. At 3, at 3 means at 9 kilopascal. At 3 means at 9 kilopascal, and these values are given. SF, Sg values are given. So my dear students, let us put these values. Now S3 is nothing but S1. Already we have seen S3 is nothing but S1, and S1 is nothing but given. S1 is given 6.6, right? So let us put here, therefore 6.6 is equal to, here SF and Sg values are given, put here. Therefore we can say SF is 0.6 plus Raynaud's fraction into Sg is 8.1 minus SF is 0.6. Now in this equation only Raynaud's fraction is unknown, therefore x is equal to 6.6 minus 0.6 divided by 8.1 minus 0.6. And if I find this Raynaud's fraction, it is also called quality, right? This Raynaud's fraction is also called quality. Then I will find this will be equal to 0.8, right? Now once you calculate this quality, let us find enthalpy at turbine exit, that is S3. Now my dear students, this S3 is equal to, we can say HF plus X Hg minus Hf, but it is at condition 3. At condition 3, right? At 3, and at 3 means at 9 kilopascal, and all values are given. Hf is given, Hg is given, X is calculated now. Hence let us put values. Therefore S3 is equal to, Hf is 174 plus Raynaud's fraction is 0.8 into Hg is 2574 minus Hf is 174. Now if I find this S3, then you will find this S3 is equal to, let us find this, you will find 2094 kilojoule per kg. This will be the value of S3. Now my dear students, here we have calculated all the enthalpies, H1, H2 and H3, all values we have now. Now let us find turbine exit. Now let us find turbine exit, that is power of turbine, right? Power of turbine. Now my dear students, the power of turbine is nothing but work of turbine. Work of turbine. Now here work of turbine will be equal to, my dear students, from 1 to 3 there is a turbine, right? But my dear students, from 1 to 2 there is total mass 100 kg, and from 2 to 3 there is 80% mass, means from 2 to 3 0.8 mass is flowing, right? Therefore the work of turbine from 1 to 2 will be, here total mass into H1 minus H2 plus from 2 to 3 the mass is 0.8 times total mass into H2 minus H3. This is how we will calculate turbine mass, turbine exit, that is the work of turbine. My dear students, here enthalpies are kilojoule per kg and mass is kg, right? Therefore from this answer we will get kilowatt, because mass in kg per second, mass in kg per second, and enthalpy is in kilojoule per kg. Now kg will get cancelled, it will be kilojoule per second, which will be kilowatt, right? From this you will get answer in kilowatt, but they are asking in megawatt, right? Once you find kilowatt, divide this answer by 1000, so that you will get megawatt answer, right? So let us put here and let us find the values, right? All the values, if I find, let us find them now. Therefore, work of turbine, that is power output from the turbine, work of turbine is equal to total mass is 100 into H1. H1 is calculated. Here I have erased the data, but you have data this, right? H1 is 3486 minus H2 is also you have 2776, right? Plus 0.8 times m means 0.8 into 100. Now here S2 minus S3, S2 is 2776 minus S3 is 2094, right? Let us find this work of turbine. Now if I simplify this, then I will get work of turbine is equal to 125560 kilowatt. This answer will be in kilowatt, right? That is power output. But my dear students, if you write this answer, you will get 0 marks because they are asking in megawatt. This is in kilowatt. Therefore, the power output, that is work of turbine, is equal to 125560 divided by 1000. This will be megawatt, and this answer you have to write in exam, type down, right? Therefore, work of turbine is equal to, if I simplify this, it will get 125.56 megawatt. And in fill in the blanks, you have to type this answer. That is, your answer must be 125.56 because already unit is mentioned. Thank you, dear students. In next lecture, we will see one more numerical on this topic.